So in this lecture, we will learn how to read the PB shed structural drawings. So here we have in front of us is a full-fledged PB structural drawing. So on the top, we can see that this is the plan view. That is, shed is running from grid 1 to grid 13. The distance of the spacing between two frames is 7242 here, and for the next frames it is 7667, and after that in the end frame it is 7242. So the total length of the PEB shed is approximately 91.15 meter, that is 91150 mm. And along this, as we have already drawn in the previous lecture, the column is going from up to first 20 meter and then again 20 meter. Here you can see that there are some numbers here: 6 meter, 7, 7, 7, 7 meter and 6 meter. So this is basically the gable end of the PB shed. So we have basically two gable ends here, along grid 1 and along grid 13. So here you can see one gable end and this is the other gable end. Here you can see that this is the side elevation. That is, if we will see the PB shed from here. So here you can see that there are various rolling shutters here. That is, there are three rolling shutters, that is RS1, RS2 and rolling shutter 3. And there are some local canopies here also. Here we have proposed that we can provide the side bracing, and here this is the side sheeting, this is the roof sheeting. After that, this is the main structural frame that we were drawing in our previous lecture. So we have drawn this frame, that is, we have drawn a column in the middle after 20 meters, and we have drawn this no property frame. So why I am showing you here is that we need to draw the PB section property like this. That is, the property is continuously changing. The depth of the beam is low in the middle and high on the beam column junction, and the depth is somewhat high here. It again reduces here, it again increases here, and then again it reduces here, and then it remains constant for up to some distance. And here this is the same procedure. That is, the depth is constant here, after that it is increasing here, and then again decreasing here, and then again increasing here, and then again decreasing here. So basically PB sections are made up of built up sections. So to save the structural steel, we have an option to put steel into that area only in which the bending moment or shear force is high. Here on the beam column junction, as this is a fixed end condition, so what exactly happens is there a large amount of moment develops here. If we will draw the bending moment diagram that we will see in the last result lecture, you will see that the bending moment diagram is somewhat like this. That is, the bending moment is maximum here, that on the top, and then it comes on the bottom here, and then again it goes to the top here, and then again it goes to bottom, and then again it goes to top, and it reduces to 0 on the bottom. Why it reduces to 0? Because on the bottom conditions of the PB sheds are preferably pinned. It can be fixed, but in my experience I have not seen a PB structure which is fixed on the bottom. So it is a very rare case. So here most of the times the end supporting conditions are pinned. After that, this is the gable end. As I was discussing with you earlier, that the slope is kept as 1:10. So here on the bottom and here on the top, the height difference has to be 20,000 divided by 10, that is in the range of 2 meters. So this is the detailing that we do on the rafter and column junction. That is, we provide a plate here, we provide some stiffeners here, we provide some bolts here, so that 100% moment is transferred from the rafter to the column section. And this is a very important detailing that we do in the PB sections. What basically we are achieving here, we are basically tying the top as well as bottom flange of the section to the purlins. So here we have two advantages. Number one, the effective length of the purlin reduces, thus decreasing the size requirement of the purlin. Second, the bottom flange of the section is tight. That is, there will be no lateral torsional buckling on the PB sections, as PB sections are very thin and very deep. So there is a very high risk of lateral torsional buckling in those beams. So to avoid that, what we basically do is that we tie the top as well as bottom of the PB sections to the purlins to avoid the buckling. And in addition to that, purlins are also tied by the sag rods. So this is the typical detailing of the sag rod connection. So now we shall start with this. That is, we need to define the sections here. So before that, we need to define the material properties. Left click on add new material. We can go to India, steel, Indian, and Fe345. Please note that as PB sections are built up sections, so we usually used high grade structural steel only. So we select Fe345, left click on OK, and then again left click on OK to close the window. After that, we go to define section properties and frame sections. So there will be some by default section properties available. Left click on add new property. Left click again on I wide flange section. So first of all, if we want to define this sloping section, that is, the depth is high here and depth is reducing here. So what we need to do here is that we need to name this section, that is member 1 high depth. Let us say approximately 1200. Material Fe345. Total depth has to be 1200. Top flange width can be 300. Thickness can be approximately 25 only. Web thickness can be 10 mm. Bottom flange width can be 300. And bottom flange thickness can be 25 mm. Let us say we can increase the web thickness by, let us say, 12 mm, and we can increase the flange width by 350 mm. If the section is semi-compact or slender, the etabs will not show the design results. So to avoid that, we can take the sufficient margin, left click on OK, and after that we left click on add copy of property, and we change it as member 1 low depth let us say we decrease it to 750 mm with same flange and same web thickness. So left click on OK. So again left click on add new property, and then here you will find non-prismatic sections. So we name it as member 1 prismatic. (1200) to 750. That is, the height of the section is reducing from 1200 to 750. Here we name the start section as 1200 and end section as 750. So here you can see that the section is visible like this. That is, the height of the section is 1200 here and it is being reduced to 750 mm. So again left click on OK. So now we have defined this member 1 prismatic 1200 to 750, and then again left click on OK. Please save the file. In our drawing, what basically is happening that we have a single member from this point to this point. So we need to divide the member into 1, 2, 3 and 4. So we left click here, go to edit, edit frames and divide frames. Let us say we need to divide it into 1, 2, 3 and 4. Let us say we divide it into initially break into 3 frame objects and then left click on apply. So we have divided this frame into 3 objects, and now we need to select this frame and we need to divide it into 2 frame objects. Left click on apply and then again left click on OK to close. So here we can assign the define frame section to this part, that is from this part to this part. In the drawing you can see that you need to put the 1200 size here and 750 size here. So we go to assign frame and section property, and then we left click on member on prismatic 1200 to 750 and then left click on apply and then left click on OK to close. Now our main purpose is to check that in the 3D view. So we can go to view and show rendered view, and then you can see that the member size has been defined from this point to this point, that is 1200 size is here and 750 size is here. Rest of the beam is empty because we have defined the none property. So after that what we can do here you can see that the size is again increasing from this point to this point. So let us say it is increasing from 750 to 900, and then after that 900 to again 750, and then 750 has to be constant from this point to this point. So we have right now defined 1200 to 750. After that we need to define 750 into 900. So again we go to define section properties and frame sections. Left click on member 1 low depth 750. Left click on add copier property. We name it as member 2 underscore high depth underscore 900, and we change the depth as 900 mm. So left click on OK option and then again left click on add new property, left click on non-prismatic. So here start section has to be 750 and end section has to be of 900. So here you can see that now 750 depth is again increasing to 900 mm here. And we need to name this section. Let us say the name of the section is member 2 underscore prismatic 750 to 900. Left click on OK option and then again left click on OK. Select this section, go to assign frame and section property. Left click on member to prismatic 750 to 900 and then again left click on apply. We can go to view and show rendered view. So here you can see that the size decreases from 1200 to 750 and then it again increases to from 750 to 900 mm. Similarly, now in third member we need to define it as again from 900 to 750. As 750 and 900 depth both are defined, so what we can do here is that we can left click on modify show definitions, we can left click on add new property, left click again on non-prismatic, we can name it as member 3 underscore prismatic. It is being reduced from 900 to 750. So we put the depth here as 900 and end section is 750. Left click again on OK, again on OK, and select this beam, left click on apply, and we can select this beam here and we can assign it as of 750 mm depth. So let us see what we have done here is correct or not. Go to view and show rendered view. So here you can see that we have drawn the PEB beam profile as per our bending moment requirements. After that, we need to define the column here. In column, you can see that the depth requirement on the bottom is very less. It is in the range of, usually in the range of 300 to 500 mm. So what we can do here is that we can define a new section here. Left click on modify show definitions. Left click on add new property. Go to steel. I wide flange section. Name it as column. .350 depth. Select the material is Fe345. Total depth is 350. Top flange width, let us say 200. Bottom flange width 200. Flange thickness, let us say 16 mm. Web thickness, let us say 8 mm. So left click on OK. And left click on add copy of property. Column underscore 900 depth. Select the depth as 900 and top flange width as 450. We can select 300 also. Bottom flange and top flange width, and web thickness can be 20 mm. Left click on OK. We need to also define the prismatic section. So left click on non-prismatic. Select the name it as column middle. We can assign different property to the gable sections. So starting is column 350, ending is column 900. So here you can see the section profile. Left click on OK option, and then again left click on OK. So now we have column middle section here. Select this column and then left click on apply. Go to view and show rendered view. So here we have drawn a PEB section profile. That is, it is 300 here, 900 here, 1200 here, 750, 750 to 900, 900 again to 750, and then constant for some length. Left click on this close option. Similarly, we can define the beam section properties here. Before that, we need to define the column section here also. As per my experience, this column section is of uniform depth. So what we can do here is that we can assign this 350 section property here. So left click on apply and go to view and show rendered view. So here you can see that this column is uniform. Similarly, we divide this beam into 3 frame object first. Left click on edit frames and divide frames, and we do the same procedure here.